All right, so today we're going to talk about Amperes Law, which is kind of the magnetic field equivalent of Gauss's law. Gauss's law, remember, you learned after you learned Coulomb's law for electrostatics. Well, Amperes Law we learned after we learned the Biot-Savart law for magnetic field. Okay, so here's what Amperes Law looks like if you write it out. It's got this crazy integral with a circle in it. It's got a B dot product ds equals mu naught I. And that would look really, really scary if you hadn't seen something that looked almost like the same thing before, called Gauss's law. All right, so here we go. Let's break this down. First of all, do you guys remember what an integral with a circle around it means?
Path integral.
It means a path integral. Well, okay. We actually didn't talk about path integrals before. But for all you people in multivariable, you know exactly what it is. Congratulations. I'm going to go to the board for a second and kind of draw what Gauss's law was. Gauss's law said you've got kind of this surface, right, with a charge on the inside. And it said something about the flux through the closed surface. All right, so this is Gauss. Drawn a closed sphere, right? There's my Gaussian sphere. And I said, equation-wise, this was a closed sphere. So the symbol for a closed sphere or a closed shape in math is two integrals to indicate you're doing an area, and then a little loop in the middle to indicate that it's a closed area. And so Gauss's law, we said, was E dot dA. All right, so that's Gauss. All right, the electric field dotted through every little piece of area gives you, and it would equal charge enclosed divided by epsilon naught, was it, I think?
Yeah.
Something like that. Okay, so that's Gauss's law. Well, this looks an awful lot like Amperes' law. All right, but Amperes' law instead is if you had a wire loop and you took, this is called an Amperian loop. If you have a long straight wire and you did a loop around that wire, and I'm going to write the closed loop line integral around that wire of the magnetic field dotted with the length of the wire is going to equal what? Well, it's got to, instead of doing charge enclosed, we're going to do current through. So there's current flowing through this wire, right? So mu naught times the current through. All right, so it's the same basic idea as Gauss's law, except instead of doing an entire shell like you did with Gauss, we're going to just do a little loop and count the amount of current flowing through. All right, so same basic idea though. All right, so here we go. If you say that again, Amperes' law is the integral of magnetic field dot ds is equal to a constant times the current going through that little loop that you drew.
What does you have one wire?
If you have two wires going through your loop, then you have two currents going through.
So
You add up the currents. Yeah.
What if they're flowing in?
If they're flowing in opposite directions, you pick a loop like this, and you got I flowing this way and I flowing that way, both through the loop. What's the magnetic field? Or sorry, the net magnetic.
If the currents are the same, then it's zero.
And it's zero. They're going to cancel each other out, right?
But if they're different strings,
Do you subtract?
Right. Yeah. So if you had two I this way and one I that way, the net current through that loop would be I this way. Right? Because 2I minus 1I. Right? What's that? Or negative I the other way, I guess. Yeah. All right, so here we go. So how do you do a line integral? It's pretty easy. Basically, the idea is if you had B dot ds, just a basic vector diagram.
Yes.
What's B again?
These magnetic
That's
field.
magnetic field. And what's ds?
It's an arc.
A length along an arc. So the dot product of B dot ds would be B ds times cosine of theta in between. All right, so example of that. Let's say you had this orange magnetic field here. All right, orange magnetic field kind of going like that, flowing to the right. And I wanted to figure out what the quantity B dot ds was for one little piece of it. So say from 1 to 2. From 1 to 2, this is my little piece of arc, ds, right? And then my magnetic field at this point, at point between 1 and 2, is pointing to the right. So what's theta? Theta is the angle in between the ds vector and the b vector. So that little piece would be b ds cosine theta. Got it? Now, if I wanted to do it over this entire arc, which is 1, 2, 3, 4, 5, 6, what I'd have to do is I'd have to calculate b dot ds for every single point. Does that make sense?
Yeah.
And that'll give you some number, some scalar number, b dot. I don't know, what's b times length? I don't even know what that means, but it's a number, right? It's b's, all your b's times all your lengths. All right, times cosine theta. All right, fine. So that's how to calculate b dot ds. So the sum of b dot ds at each point gives you the line integral from point 1 to point 6. Good?
Yep.
And then Ampere's law basically says if you do that in a closed loop, starting here and then ending all the way around to there, the total number that you're going to get in this case is 0. Why?
0 to 2 pi. It's ending and starting with the same point if you're doing path integral, and so it'll just cancel out.
Yeah. Well, 0 to 2 pi, assuming that the B field was all straight, right? But yeah, if you did the closed loop line integral about this, you would get an answer of 0. And the reason why is because the way I did my little loop here, how many wires are going through that loop? None. There are no wires passing through this little circle I drew. Agree? And if there's no wires passing through that circle, that means b dot ds around the entire loop has to be 0. Does that make sense? There's no current flowing through this little line that you drew, this little circular line. The net b dot ds has to be 0. All right, so that's Ampere's law. All right, blah, 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 blah. Here's how we use Ampere's law. That was the theory. Here's how you use it. By the way, Ampere's law, you're going to hopefully get a little comfortable with this in this class. And then when you get to multivariable, if you aren't in it yet, you're really going to understand it well because you're going to do a lot more with it. All right. So here we go. You've got a current flowing through a wire. And I want to know how strong the magnetic field is at a radius of r. So what do? Just like Gauss's law, we draw, instead of a Gaussian surface, we draw an Amperian loop of radius r. Okay, so here we go. Integral b dot ds equals mu naught I. Well, b dot ds, how big is my total loop?
2 pi r.
It's 2 pi, it's the circumference, right?
Mm-hmm.
So 2 pi r. So b dot 2 pi r. Oh, by the way, what's theta?
You did
9 degrees.
0 degrees. Why is it 0 degrees?
Cosine.
Why is theta?
Oh, 'cause with the-
Yeah, what direction? Let's see if I can draw on here.
Wait.
The magnetic field
cross
is
product
going to
is
be.
sine theta, dot product is cosine.
Let me. Oh, it will let me zoom in. Awesome. Okay, here we go. So let's pick a point on the wire right there. You guys all see that point?
Yeah.
All right. At that point, what direction is the field going? No, it's not going
No,
up.
It's going.
Around, kind of?
It's going around in this direction.
Oh, wow.
Yeah.
So it's
The field is pointed that way, agree?
yeah.
At that point, what way is the Amperian loop facing?
What?
Well, I drew a loop, right? What way is my finger going?
It's going in that same
The
direction.
other
It's,
way?
oh shoot!
Oh.
Ah!
Undo.
Panic. Undo. Oh, awesome.
Pause the recording.
Okay, so would everybody agree that at that point, at the point marked in red right here, that the magnetic field is pointing in the direction of the arrow? Agree? So here's the other question. What direction is ds pointing in? Because remember, it's b dot ds, right?
Well,
So let's do that in blue. What way is it pointing?
it's either it's with it.
It's same direction. Why? Because ds is the direction
But you applied the circle.
that I drew the circle in.
Oh, doesn't that mean that only would the charge at the center of
The charge?
I don't know how to say it.
We aren't talking charge anymore because we're not talking Coulomb's law.
Current at the center of the loop is the only one that matters then, because all the other circles would be like parallel to these circles. Because like when you
Ampere's law talks about if you draw any loop, it's like Gauss's law. Gauss's law, we always put the charge right at the center, but it still works even if the charge is off center. Same thing with Ampere's law. We say that the current running through the loop is running through the exact center of the loop, but it also works even if the current is off center.
so the
But it makes the math really freaking hard if you put the wire off center from the loop that you draw.
okay, because the magnetic field.
Right, because the magnetic field strength is changing, and the angle between ds and B is changing too. Right?
So that'd make it far more.
Right, so that's why we don't do that.
Okay.
Right? I mean, you could if you had a computer and you wanted to do a whole bunch of crazy math, but when we're just doing it in class, it's way, way easier to set it up so the wire runs exactly through the center of the loop. And by way, way easier, do you remember when I said you have to do this problem and figure out the magnetic field from a wire using the Biot-Savart law, how many lines of work that was? You had to do L'Hopital's rule. You had to do that crazy integral thing. You had the over something x squared plus r squared to the 3/2 or something like that. Guess what? It's one step using Ampere's law. One line. That's it. Here's the line. Because B and ds are pointing in the same direction, what's theta? 0. What's cosine of 0? 1. So it's B times 2 pi r times 1 equals mu naught I. What's B? The answer is mu naught I over 2 pi r. Done. That took us a whole page in the notes before. So we like Ampere's law, just like we like Gauss's law. Yeah. So, and of course, just like Gauss's law, it's only really useful for certain shapes. Shapes that it's easy to draw a loop around. So the shapes that we're going to care about is straight wires and coils of wire, or actually solenoids. Do you guys know what a solenoid is? It's one of those wire wrapped things. Yeah, it's basically looks like this, made of wire.
It's for the
That's a solenoid.
AM radio.
Huh?
Crystal radio.
Sure. Or like, yes, like we're going to play with tomorrow. So anyway, a bunch of loops of wires it's called a solenoid. All right, so let's scroll down, go to the bottom. Haha, here's where it gets interesting. Here's where it gets interesting. What if you wanted to figure out the B field inside of a wire? Have you ever thought about that? We know that a wire produces a magnetic field, right?
Yes.
So I need a thick wire. Where's a thick wire? Here's a thick wire. Here, see this wire? It's a big piece of metal. It's about a half an inch in diameter. And then we could run current through it, right?
Yeah.
So if we ran current through this wire, we know there would be a magnetic field outside, but would there be any magnetic field inside?
I would assume so,
Yeah.
because we have to calculate it.
It would have to be because it's a source.
It all depends.
Oh, okay.
If you were to look at a cross-section of a wire, here's a wire like that. Where are the charges actually moving? Are they only moving along the surface of the wire? Or are they moving in the middle as well?
Depends on the type.
Discuss. Discuss. When you send a current through this wire, are the charges all moving along the edges? Or are they moving in the middle too? Okay, take 30 seconds and discuss amongst your table. All right, raise your hand if you think that current flows inside the whole wire throughout the bulk of the wire. The charges, when the charges are moving in a wire, they're moving not just on the surface, but throughout the middle of the wire too.
Oh, so
Raise your
both.
hand. So about
Both.
most of the class. Does anyone say no? Charges move only on the outside of the wire.
Where's your raising your hand?
And about 5 people. Okay, so
Can
for
we
the
do the
people
answer
who
C
say,
both?
the people who say charges are only moving on the outside of the wire, can you give me a good physics explanation of why that would be? Only on the outside. Yes.
Because charges are electrons holding electron
I love that answer. Electrons are all negative, right? Doesn't that mean they repel each other?
So they can't spin as far.
And we learned in electrostatics, what did we learn? One of the rules was conductors in electrostatic equilibrium, all the charges
Go to the
go
outside.
to the edge, right? They try to get all on the outside. And so you could therefore argue that all the current in a wire is all along the outside of the wire. All right, does anyone have a counterpoint to that?
AC current. There's not enough.
They're all being attracted.
Yes, I like that counterpoint too. They're not attracted to each other, but what if you're trying to push so many charges down that the only place left to go was the middle? You can't fit all the charges on the outside. It turns out both answers are correct under different situations. Under DC, under direct current situations. Well, actually, let me explain it this way. If you have a circuit and you close the switch and send charges through, where will the initial pulse of electrons go?
Yeah, so.
If you only have a couple electrons, well, where will they go?
All to the outside.
They will all go to the outside preferentially. They'll all repel each other. But then when you start pushing a whole bunch through, what happens?
They'll clump
They'll
up
get
in
harder
the,
and
They
harder.
everywhere.
start
Get on the
filling up
outside.
the middle too. Does that make sense? So it turns out that under direct current situations, that circuit's actually been on for a long time. And by a long time, I mean at least like 10 nanoseconds. Right? So the current's been going for a long time. After a while, they've got no choice but to start moving through the middle. But for high frequency alternating current, that's flipping back and forth and back and forth and back and forth and back and forth. Well, the charges go this way, and then the charges go that way, and this way, and that way. You never have enough time to get the charges flowing down through the middle of the wire. So that was the thing you were talking about before, skin effects. All right? High frequency AC, all the charges move along the outside, whereas DC, they move through the middle of the wire. Now, in this class, we aren't going to really talk about high frequency AC at all. We're just going to talk all the problems we're doing so far, with the exception of some of the RC circuit questions were all pure direct current questions, right? So, in this class, we're going to pretend like charges are evenly distributed throughout the bulk of the wire as they're moving. And therefore, we have to use Ampere's law in such a way. Oh, let's see. If you had a wire like this, say it was like 10 inches in diameter, right? And all the charges were on the surface of the wire as they were moving, how much magnetic field would be in the middle?
None.
None. Why?
Because
there's no charge. There's no current.
There's no
enclosed.
current enclosed by your loop as the charges are moving through. It's just like Gauss's law, right? There's no charges enclosed, there's no electric field. So, but if you have charges flowing throughout, depending on how big you make your loop, you're going to enclose more charges, right? Which means you're therefore going to have a magnetic field that's going to get bigger and bigger and bigger as you get further and further away from the center. Does that make sense?
Yeah.
All right, so here it is. B field inside a wire. You have to know about the current density, right? You have to know how many charges are moving per area, or current through area. You have to know the total current. You need to know the area of the wire. You do Ampere's law. And calculate the charges flowing through our little dashed loop right there. Well, the current flowing through that little dashed loop is going to be the area of the little circle times the charge density, right? And so in the end, you get little r squared over big R squared times the current. All right? And plug that in, and you end up with the magnetic field inside the wire is mu naught I over 2 pi big R squared times little r. What's little r?
The little radius of the little circle.
How far you are from the center. All right? And so we graph it just like we did with the Gauss's law ones, and the graph looks the same. All right? Same as the electric field graph, except for on the inside it goes linear. On the outside it's actually 1 over r rather than 1 over r squared because it's a wire instead of a point. All right? Last one, solenoids. This is the tricky one. It's the one that shows up on AP tests a lot. You ready? Here we go. Let's say we wanted to know how strong the field was in the middle of a bunch of coils. How do you do that? This one is goofy. You ready? Dino, you ready? All right, let's do it. I don't know if you know this, but inside of a solenoid, the field is mostly uniform. Do you guys know it? Raise your hand if you knew that. Inside of a solenoid, field is mostly constant. All right. Now, if this were an infinite solenoid, what would the field be? Perfectly constant. It would just be a bunch of straight lines. There'd be no edge effects at all. Just like a capacitor, right? All right, so here's how you calculate the B field inside of a solenoid. Could you imagine doing this with Biot-Savart law?
No, it would be horrible.
It would be horrible, but you actually could do it. You actually did do it, and you're going to do it again on the quiz on Friday.
Oh.
Just for one loop.
Oh. Okay.
What if you had 50 loops?
Then you just do it 50 times.
You'd have to do the whole thing 50 times and add them all up. And it would be awful.
Be gross.
Guess what? 50 loops using Ampere's law is a piece of cake. So here's how we do it. What we do to draw our little Amperian loop, we draw a loop that has an edge along the inside parallel to the field, an edge along the outside where there's no field, and an edge here and an edge here. Does this edge and this edge count, Shrina? What do you think? This is totally a leading question.
Hey, yes, true.
I like the no part of that answer. Yes, I like that answer. They don't count. Why?
Because they're parallel to the...
Parallel?
Not, they're perpendicular.
The cosine is, it's 90 degrees, and cosine of 90 degrees is 0.
Right.
So this ds is perpendicular to that b, which means that that 90-degree angle makes the cosine 0. right, so this edge doesn't matter. This edge doesn't matter. This edge doesn't matter because there's no field out here. So the only edge that matters is this little piece along the inside. So B dot ds is B times L for this piece, plus 0, plus 0, plus 0. All right? So B times L equals mu naught times Ni. All right? Therefore, the field inside of a solenoid is mu naught Ni over L. Done. How many people memorized that last year? You did it last year, but we just gave it to you. Didn't explain why. But this is why. It was on, yeah, it was on the equation sheet last year.
And do you just make L the length of the solenoid?
Yeah. L is, for the purposes of the analysis, L is the length of your the line, the dashed line that you drew. But the reality is, what matters is the field inside of the solenoid depends on only two things: the current and
The number
the loops per length of the solenoid. The loops per length of the solenoid. N divided by L. Shiv, did you get that? What matters for a solenoid is what two things? The amount of current and loops per length. What does loops per length mean?
Like, how many loops you can fit in a certain amount.
How tightly wrapped the loops are. So if you want a stronger solenoid, you have to wrap the loops tighter.
What if you wrap them over each other?
If you wrap them, that's one way to do it, right? Because you get more loops per length of the solenoid.
You
Yeah.
wrap them around like, say a nail, doesn't that make one kind of electromagnetism?
That changes your mu naught. Because mu naught is for a vacuum, but a nail,
Oh, so it's like
it's like the equivalent of a dielectric for a capacitor. Right? Mu naught is for a vacuum, but mu times something is for a nail.
Even if it's an iron nail.
It's an iron nail. It's awesome. All right, and that's it.